Welcome to lecture number 26. Today we'll study Thevenin's theorem for AC circuits. We have already studied Thevenin's theorem for DC circuits. The steps are the same even for AC. If you want to revise Thevenin's theorem for DC circuits, you are referred to my lecture present on my available on my YouTube channel that discusses Thevenin's theorem for DC circuits. It also discusses these steps in details, right? The steps are the same even for AC. We'll first remove this ZL. Here we call it ZL, the impedance of load. In DC circuits we call it RL, the resistance of load, because it is always resistance in case of DC, but here it can be a resistor, capacitor or inductor or a combination. Then we'll find in step 2 we'll find Z Thevenin. In DC circuits we call it R Thevenin because it is always R there, but here it can be R, L or C. And then we'll find V open circuit and then draw an equivalent circuit and find the unknown quantity. Here is an example circuit given where we have a voltage source, a current source and these three passive circuit components, and we need to find voltage drop across this 2 ohm resistor. So we'll apply step number 1. Step number 1 is to remove load. Let's remove load. This 2 ohm resistor is our load. Why is it load? Because we have to find voltage drop across it, right? So we'll remove this load, and now we have this end, these ends open, and we'll find voltage drop across it. That will be the VOC, and then we'll find Z Thevenin. Right, we'll do it like this. In fact, find VOC first and then find Z Thevenin. Right, VOC. To find VOC, we can either apply loop analysis or nodal analysis. Let's apply nodal analysis first. This is minus J2. There is a capacitance here minus J2 ohm with capacitive reactance minus J2. So we have removed load and now we are ready to find VOC. Assume a voltage V here, and then we have only one non-zero node. We'll write equation for this. We'll write KCL equation for this node, Kirchhoff's current law equation. We'll assume, if we do not know the exact direction of current, we'll assume to be moving away from the node. V minus 24 at an angle of 0 divided by 2 is the current that moves in this branch away from this node. And the current that moves, since this has a current source, we have to take it exactly what it is, but this is minus 2 at an angle of 90 because it is entering, and we have already studied that all entering currents are taken as negative. In this part we don't have any current because open the other side, so we have a 0 current here, and then it becomes equal to 0. So we can multiply the whole things by the whole equation by 2. This is B minus 24 at an angle of 0 minus 2 2s are 4 at an angle of 90 is equal to 0. So we can be written as 24. Take on the other side, 24 at an angle of 0 means 24 plus 4 at an angle of 90. Since 4 at an angle of 90 is a polar number, and to add these two numbers together, this has to be in the rectangular form. 4 at an angle of 90 can be conveniently converted into the rectangular form and can be written as J4. So this is 24 plus J4. And this voltage is the same as this voltage because the voltage drop across this minus J2 ohm capacitor is 0. So this is the same as VOC. So we have computed, we have removed CL, we have computed VOC, and now we are ready to find Z Thevenin. To find Z Thevenin, we have already studied that we replace these sources with their internal impedances. The internal impedance of a current source is very large, so it is replaced with an open circuit. We have already studied in case of DC, and the internal resistance of this voltage source is very small, so it is replaced with a short circuit. Right. So here this J2 inductor hanging in air, so it has no use, and At these two terminals, we need to find out C Thevenin. We cannot call it R Thevenin because it involves resistor, inductors, and capacitors all. So that is why we call it Z Thevenin. And Z Thevenin is 2 minus J2 ohms. So now we are able to perform the last step, to draw equivalent. To draw an equivalent where we have a voltage source whose magnitude is equal to VOC, which is 24 plus J4 here, and in series with an impedance that is equal to Z Thevenin, 2 minus J2 ohms. And finally, this is the Thevenin's equivalent, and then we finally put the load resistor that we removed, the load impedance that we removed in the first step. See, and in this case, it was 2 ohms, I guess. Yes, 2 ohms. And we were required to find the voltage drop across this 2 ohm resistor. So now it is very straightforward to find this voltage drop. We can apply voltage divider theorem, because we have to find voltage drop across this 2 ohm resistor. We have these two components connected in series and this voltage source supplying them. So we write the resistor or the impedance across which we have to find the voltage divided by the sum of the two in the denominator times the input voltage, 24 plus J4. So this 2 plus 2 becomes 4. This is 4 minus J2. Take 2 as common. This becomes 2 minus J1. Cancels with this one. So we have 24 plus J4 divided by 2 minus J1. These two numbers are in the rectangular form. They cannot be divided easily, so we convert them into polar forms. So once converted into polar form, this is 24.33 at an angle of 24 plus J4, 24.33 at an angle of 9.46 degrees divided by 2.23 at an angle of minus 26.56. And we have already studied how to convert these numbers in rectangular, how to interconvert between rectangular and polar forms. So the answer is 10.91 at an angle of 36 degrees. So this is our answer. This is the required V out. In the lectures to come, we will study more AC circuits and apply different techniques that we studied for DC before. Thank you.